So hi, I'm Gabriel Munoz I'm a postdoctoral fellow at the University of Montreal and under the mentorship of Professor Sébastien Sauvé from University of Montreal and Professor Jinjia Liu from McGill University. And I would like to thank Thermo Scientific for this invitation to share our results of the assessment of novel fluorochemical pollutants at firefighting foam impacted sites. So a word on the aqueous film forming foams, also abbreviated as AFFFs. So such formulations are high specificity firefighting foams. They've been around since the 1950s and they've been designed to fight oil-based fires. They're commonly used in firefighting training activities such as for the regular testing of sprinkler systems in aircraft carriers, also for the training of firefighters, for instance, by the application of these foams in such airplane fuselage structure lights. IFFFs are also used in emergency response to major oil fires, such as those occurring in the aftermath of aircraft accidents, also of oil refineries, and during accidents during the transportation of petroleum, for instance, through rail convoys. The aqueous film forming foams are commonly composed of hydrocarbon surfactants, also corrosion inhibitors and foam stabilizers. The key ingredients to AFFFs, however, are the highly fluorinated surfactants that help create a thin film at the fuel foam interface that is impervious to volatile fuel vapors and also deprive the fire of the oxygen, which prevents fire reignition. And one of the most used and studied PFAS in AFFFs is actually perfluoroalkyl sulfonic acid, or PFOS. The PFAS are the highly fluorinated surfactants, so they are man-made compounds. They've been manufactured since the 1950s via two major synthetic pathways, electrofluorination and telomerization. And since the steady increase in PFAS production from the 1970s to the 1990s, it was foreseeable that such compounds would finally emerge as environmental pollutants. And this was demonstrated for the first time in 2001 by GZ and Cannon, who evidenced the global distribution of PFOS in aquatic species around the world, showing the bioaccumulation, long-range transport, and bioaccumulation potential of such compounds. Since there have been a global restriction toward the global ban of PFOS, as early as 2000, the 3M company announced the phase-out of PFOS and POSF, and in 2009, PFOS was actually added to the Annex B of the Stockholm Convention on POPs. As of the case of Canada, there are also current shifts toward non-PFOS-based form. In 2002, Canada ceased importations of PFOS-based AFFFs. However, the remaining PFOS-based AFFF may still have been used until May 2013, when the removal of all the remaining stocks should be completed and the use of PFOS-based AFFF prohibited. So as a summary on PFOS and AFFFs, the PFOS and the other long-chain perfluoroalkyl acids are global contaminants of aquatic environments. They're persistent, toxic and bioaccumulative, and they can be biomagnified in food webs. This has led to the phase-out of PFOS in AFFFs, and major industries have been shifting toward non-regulated alternatives, such as the short-chain PFAS and even other chemistries, such as the betaine-based PFAS and non-fluorinated alternatives. So now we move on to the rationales to the present study with the key knowledge gaps. So first, the monitoring surveys have often been limited to PFOS or PFOA, or even a suite of perfluoroalkyl acid, which may yield conflicting results when looking at the mass balance. For instance, the degradation of precursors such as the N2-FTAB compound, which are not routinely monitored, may actually lead to increased perfluoroalkyl acid levels over time, which questions the reliability of environmental assessment when precursors are not captured by the current analytical methodologies. Second, the environmental fate of the newly identified PFAS is vastly unknown. There have been limited studies on toxicity, bioaccumulation, or migration from AFFF impacted sites for those newly identified PFAS. And finally, there was a question whether the pre-existing analytical methods for PFOS or PFOA would be transferable as is for a wider range of analytes. Since there is a current lack of standards, it would preclude the quantitative performances of such method. And also, matrix complexity could also alter the method recovery from the sample. So, in this context, our overall research questions are as follows. We would like to determine whether PFOS phase-out was effective in Canada, and if so, what alternatives are being used. Second, should the list of routinely monitored PFAS be revised to a larger breadth of compounds? And finally, how efficient and reliable are the current PFAS analytical methods? The specific objectives are delineated hereafter. We first wanted to identify the PFAS present at an AFFF impacted site. Second, to validate analytical methods for the newly identified PFAS. And third, to determine whether the PFOS ban on AFFFs is being effective in Quebec. So first, in order to answer our questions or hypotheses, we need to choose a relevant study site. As it happens, there was a study site from Québec, Canada, that was recently impacted by a major oil fire, and there were AFFFs deployed in order to control that fire. The AFFF impacted site is located in the Chaudière River watershed. The Chaudière River, which is here, actually has its headwaters near the Mégantic Lake and meanders over more than 200 kilometers before discharging into the St. Lawrence River just opposite Quebec City. It should be mentioned that the watershed is a sparsely populated catchment with very low urban or industrial pressures, so such pressures should not have been a confounding effect in the evaluation of the initial AFFF peak at this site. The railway accident, for that is the subject under discussion here, is the result of an unfortunate series of errors that led to the derailment of 63 out of 72 tank cars and the spill of 6 million liters of light crude oil downtown, after which 33,000 liters of AFFF concentrates were deployed. And actually, all of the white residues that you see here, close to the derailed tank cars, are actually the AFFF residues that were applied by the firefighters at the site. Moreover, the actual date of the accident is also relevant. Coincidentally, it happened just about 1 month after the PFOS ban on AFFFs came into effect in Quebec, so thus would mean that this would be a relevant case study in order to answer out a question on whether the PFOS ban on AFFFs was being effective. The railway accident site is located just in downtown, a small municipality of about 6,000 inhabitants, with the Mégantic Lake to the south and the Chaudière River to the east, which takes its source near the Lac Mégantic Dam. There were some great remediation efforts in the aftermath of the accident in order to remediate the hydrocarbon contamination. For instance, the TPH levels were quite high and the sediments close to the outfall site, and also the polycyclic aromatic hydrocarbons and volatile organic compounds. Since AFFFs were applied in order to control the fire, it was postulated that a portion of the AFFFs may have entered the aquatic ecosystems in the Chaudière River watershed, which provided the grounds for the present study. So a word now on the sampling design. We targeted 3 different matrices: sediments, fish, and soil. The sediments were collected in the summer 2014, both close to the accident site in the Lac Mégantic Marina and the Chaudière River, but also following a gradient along the Chaudière down to 92 kilometers downstream from the outfall site. As for the fish, a number of fish samples were collected through a series of sampling campaigns following the accident, and coincidentally, we also had access to archived fish samples from the same area, but 2 years earlier, meaning that the samples could be used as a reference prior to the accident. And as for soils, 3 different sets of samples were used. First, soils collected after the accident in 2013, close to the accident site. Then it should be also mentioned that a lot of the soil on site was excavated in order to be treated off-site in nutrient-amended biopiles in order to remediate the hydrocarbon contamination. So we did have access to some of those biopile samples too. And finally, we also collected samples from the fire area sampled in 2015. A single instrumental method was used for all of the 3 matrices with very low matrix effects, using a thermodynamics Ultimate 3000 LC chain, a thermoheated electrospray ionization source, and a thermo Q-exactive OP-trap mass spectrometer. The chromatographic setup consisted in a Hypersil Gold analytical column for PFAS separation. Also note that the PFAS trap column was positioned after the aqueous mobile phases mixing point, but before the injector as a delay column. The ionization source was operated in fast polarity switching mode and mass spectrometer in full scan MS mode. Depicted here is the ultra-high performance liquid chromatography gradient program applied for a total runtime of 14.5 minutes. The mobile phases are specified here, being HPLC water and acetonitrile for the aqueous and organic mobile phases, respectively, using formic acid modifier in order to promote the analysis of the positive mode compounds, such as the betanes. The chromatographic performance was excellent, being separated, for instance, the whole range of perfluoroalkyl acids from the 3 perfluoroalkyl carbon atoms bearing PFPA down to the largest chain congener between 2.1 and 10 minutes. So the negative and positive mode analytes were actually acquired within a single run with excellent retention time stability, less than 1% for more than 100 real samples. And the mass accuracy was also excellent. Depicted here is our list of 30 model analytes that were used for quantification, validation purposes, and even semi-quantification of some of the newly identified compounds. We targeted both the historic or old compounds, if you will, such as perfluoroalkyl carboxylates or PFOS, but we also had access to different standards that were custom synthesized at the Surfactant Institute to provide relevant compounds for the semi-quantification. And those included novel chemistries such as the betaine-based PFAS, the amine oxide-based PFAS, the quaternary ammonium-based PFAS, and the amine-based PFAS. The quantification strategy is illustrated here for fish. We used matrix-matched calibration curves using spiked aliquot of real fish samples with incremental levels of PFAS, and after an equilibration time, the samples underwent the full preparation procedure and the calibration curves were built using an inverse weighted linear regression fitting. The quantification performance for fish showing the method limits of detection in the range of 6 picograms per gram on a white weight basis up to 180 picograms per gram. It should be mentioned that those were derived from the matrix match calibration curves, meaning that any recovery losses would be already integrated into the method limit of detection determination. We also evaluated method trueness through the analysis of a standard reference material from Lake Michigan, and the values found in the present study were in excellent agreement with a reference value by Reiner et al., which is itself based on an international interlaboratory comparison exercise. Depicted here are the concentrations observed in the different fish samples from 2 years before the accident, from the different sampling campaigns that were conducted in 2013, the year of the accident, and 1 year after. And if you focus on the PFOS, where first you observe that the concentration is quite low, and also it doesn't change through the different sampling years, which strongly suggests that the firefighting foam applied were not PFOS-based. We have been talking about the method detection limits, how the calibration curve were generated, and also about the method trueness. However, it is also important to document the actual method recovery from the different matrices. And in the particular case of the soil samples from 2013, we were concerned that the presence of oil co-contamination could possibly affect the analytical method performance, especially for the sample treatment part. So in order to assess the influence of oil co-contamination on the recovery fraction of the different PFAS, we used a sandy loam soil, which is similar in texture to the actual soil that was exposed to the major impacts. And we spiked the soil with two oil co-contaminants, diesel or back-end crude oil, which actually corresponds to some oil that was collected from the derailed tanks. If you focus on the perfluoroalkyl acid, you see that there is a relatively limited range of recovery values, even when the oil co-contamination was added, implying that there was a relatively low effect of the oil co-contamination. And looking at the recovery numbers, those were quite good. However, for some of the newly identified PFAS, such as the betaines, the recoveries were lower, and we are currently working on improving the recovery method. The results for the model PFAS in soils showing a sharp reduction in PFAS levels from 2013 to 2015, as well as concomitant decrease of TPH, which was achieved thanks to excellent remediation efforts. If we have a closer look at the molecular pattern, we see that the 6,2-FTAB as blue bar and 6,2-FTSA as dark green bar are actually quite prevalent in the profile. And if we focus on this particular sample, you see that 6,2-FTAB, so a compound that is not included actually in most of the routine monitoring surveys, actually exceeded the PFOS concentration by a factor of 200. Some suspect target analysis was also conducted, and a suspect target list of more than 100 PFAS was designed based on the literature from AFFF formulations. We used either full-scan MS or high-resolution MSMS experiments in order to get a higher identification confidence level. And here are the different criteria that we use regarding the peak intensity, the exact mass accuracy, the observation of an expected retention time based on the known hydrophobicity of the molecule, the observation also of retention time patterns in the series of different homologous samples, homologous analytes, and also the elucidation of high-resolution MSMS fragments. The suspect target analysis is illustrated here for the sediment samples, and should be stated that it is the first-time identification of several cationic and zwitterionic fluorosurfactants in any real environmental samples, and this was achieved thanks to the Orbitrap technology. Here you can see the different families of compounds, the fluorotelomere sulfonamide amines, and some of the betaine-based PFAS as well. And if we focus, for instance, on the fluorotelomere sulfonamidoalkyl amines and look at how the different identification criteria were fulfilled or not based on the aforestated criteria, you see that the full-scan MS intensity criterion was fulfilled for all of the three analogs, and the exact mass accuracy was excellent, being below 1 ppm for all of the different analogs. You can also see that the retention time pattern were highly congruent with the increase in hydrophobicity as we increase the number of CF2 units in the molecular structure. And finally, we were also able to confirm the structures by doing some high-resolution MSMS experiments. And here for the 6,2-FTA, for instance, we were able to fit those fragments to the observed masses. And it should be mentioned again that this was achieved even with a relatively low concentration in the sample, which again illustrates the very high capability of the Orbitrap in order to perform qualitatively. A semi-quantification approach was also engaged in order to have a first idea of how the qualitatively detected compounds would compare from our list, extensive list already, of 30 quantitative model PFAS. So now I'm going to operate a change in the y-axis, and what you see here are the semi-quantified concentration of the 55 additional semi-quantitative PFAS, showing again that even when concentrated on an extended list of standards, we would still greatly underestimate the total PFAS contamination at a newly PFAS IFFF impacted site. And here are some of the structures of the newly identified PFAS, including betaine-based PFAS here in the yellow, blue, and red bars, and green bars. Again, if we classify the samples based on sampling year for the soils, you see a near total dissipation between the 2013 and 2015 samples. And if we focus now on how much PFOS would represent on the total PFAS, meaning the quantitative and semi-quantitative PFAS, you see that now it only represents 0.02% of the total PFAS amount, showing again that with the great underestimation potential of studies only focusing on PFOS, PFOA, or even an extended suite of perfluoroalkyl acids. So in order to conclude, we were able to identify some of the PFAS present in AFFF impacted samples. Of course, we only performed a suspect target analysis, meaning that many more PFAS could be there in the samples. The analytical method were validated for the newly identified PFAS, showing excellent instrumental performance, both qualitatively and quantitatively. However, the extraction part, so from the extraction from the sample of the newly identified PFAS, was more challenging, and we're still working on it. Finally, as PFOS only represented a minor proportion of the total PFAS and the PFOS levels did not increase in fish after the accident, this provides an indication that the PFOS ban is being effective in Quebec. I would like to acknowledge the co-authors of this study, Mélanie Desrosiers from the Centre d'Expertise en Analyse Environnementale du Québec and Québec Ministry of the Environment, Sandra Mejia from McGill, who is actually the lead author for the soil study, and Dick Chalieu, also from McGill, Pierre Labadie and Hélène Budzinski from University of Bordeaux, and Priscaré, Sung Vauduit, and Sébastien Sauvé from University of Montreal. Thank you for attending, and thank you for your attention.